this morning was really, really cold.
I feel you on that. I had to put a sweater on for this lecture.
I know. I have my sweater on too. I'm like, oh my goodness, really? Mm-hmm. Anyways, it is what it is. Hopefully we'll have a cold Halloween. And then it might be coming back up at the temperature. Alrighty. So it's 2:30. Let's go ahead and start. I'm putting, you have the agenda on the screen. We're going to continue with air pollution. I really hope that all of you have already or are reading. If you haven't finished reading the chapter, are reading. The air pollution chapter is very lengthy, has a lot of information. And for the risk quiz on November 2nd, you are going to use your risk notes or reading notes, remember? So this is what I'm going to be doing. I am going to open an assignment for the reading notes before the quiz so you don't spend time on uploading those. Okay? So I'll send an email on Sunday night or to let you know when it's open. So whenever you finish them before the quiz, please submit them. And then on Monday, what I want to, I was talking to someone that came to the office hours and was talking about the project. I would like everybody to know what projects all the teams are working on. So it's not going to be a lot of work. Just one slide on Monday, very quickly, and no more than a minute tops. Every team is going to be sharing this one slide, decide who's going to do it, and I want you to share what's the proposed title or the topic, and just briefly mention where you are at and what is going to be done coming up. So that just came up today based on some questions that were asked during office hours, and I thought that it was a good idea to share with everybody, that everybody share what you guys are doing. There are good projects in there, and everybody will know what's going on, what to expect later in the semester. Alrighty, and next week is going to be our midterm on November 4th. So we know, and then a holiday is coming. All right. So we're going to continue with, with the air pollution. I'm sorry, I looked around and opened the screen and there was a lot of students in the waiting room. Okay. Can I stop sharing? Yes. So I'm going to go back to the PowerPoint. And if while I'm teaching, anyone knows of someone that might be in the waiting room, please, I will appreciate you can let me know. Feel free to stop me, just speak up loudly, is fine, don't worry. In the chat is good too, but sometimes I don't look at the chat where the chat is. I'm writing or something else, and sometimes that's why it could take me some time to look at the chat. Hopefully they will update that on Zoom soon. So we were talking about air pollution. I'm gonna share the PowerPoint. I'm gonna share my screen and we'll continue there. And after finishing some things on the PowerPoint, we're gonna go to the whiteboard. And then we might need to come back to the PowerPoint again. But then we're gonna be doing some problems. So we'll see how much. Can you see my screen?
Not yet, Professor.
Oh, what's happening? It's supposed to be sharing. Okay, let me try it again. Okay, now it's there, I think. I'm telling you, my computer is getting old. I had to restart it again and hopefully it won't give us any issue. Okay. Okie dokie. So we already talked about this. I'm just gonna move forward with here. That's where we stop. We stop at the major pollutants in the air. We're going to be observing standards. So the government has set up standards for these contaminants or pollutants, and also we're gonna be addressing these contaminants through design and different aspects. So we're gonna be first of all talking about the policies or the regulations. So what we have in here is a table that shows the air quality control regulations. It's a history of how they were developed and how many different volumes, or they call them titles, are there. And the last one, title 9, is going to be related to clean air research. So actually a lot of funding has been set aside to do some research related to clean air and how we can reduce the emissions from different waste from the cars and other devices at home that we're producing and are resulting on contamination on the environment. So I'm just going to be focusing my attention to the main two things that are shown in here are the National Ambient Air Quality Standards, or the NAAQS. They're going to be focusing on the air quality standards for some pollutants, the pollutants that I just showed you. And we're going to be talking about primary and secondary standards. We're going to explain that pretty soon, and where we're going to be finding what they are. I'll show you a table this coming, and how they are divided. But also, we have Title 3 that is going to be related to the reduction of the emissions of hazardous air pollutants from major sources. What does that mean? Is going to be related to point source pollution, and we're going to explain more on the board about what is a point source, non-point source pollution, in case that you haven't talked about that in some other classes. This is the class that we take the time to review a little bit what is that. So examples, if we have an industry that is emitting some toxic chemical, it should not, a gas with toxic chemicals, it should not be released without treatment. So that's when we're going to be coming up with some design or pollution control device to ensure that we can mitigate that source coming from industry. So we're going to be talking about that. Ambient air quality standards is going to be just the quality of the air that is going to be harder to control or to remediate, or the emissions. Emissions are just released into the environment, and we can identify those points. And by identifying those points, we can do something about it. And it can, we'll talk about the different options in there. So how do they look like? If we put some numbers on it. The primary national ambient air quality standards are here. What the standards tell you, it's a given concentration that should not be exceeded. And in case of the air quality, it's going to give us a time of contact that should not be exceeded. For example, for CO, it says that 8-hour contact should not be exceeded more than once a year, and the maximum concentration is going to be 9 ppmv. And remember, for gas concentrations, we use a little v at the end of the ppm. Now, if you notice, for CO, there is also a 1-hour contact, and the 1 hour is going to be a way higher concentration, 35 ppmv. So this is what when we're talking about acute exposure, a sudden exposure, a higher concentration is going to be different depending on the chemical that we're talking about. And if it is exceeded, the standard is exceeded, then probably could result into death or some non-reversible harm. So it's important to observe these air quality standards. We could be on the freeway driving around, and if we are for an hour in an area where the concentration of CO is 35 ppmv or very close to it, it could be bad for your health. And you can see in there that we have NO2, SO2, lead, PM, particulate matter, and 2.5 means 2.5 micrometers. So it's a very tiny particle. And PM10 is a particulate matter that is 10 micrometers in size. So those two are the particles that are going to be regulated. They're very, very tiny, and they're really damaging for your lungs. That's why they have to be regulated. And also we have ozone in there. So we talked about these chemicals in the previous table, and we showed the health effects and where they could be coming from. And this table is a primary national ambient air quality criteria, and shows you what are the maximum concentrations and the maximum time that you could spend there in average. The primary pollutants or these standards are directly discharged into the environment. And we'll talk about what is the difference with the secondary pollutants or the other standards. So the primary pollutants and primary air quality standards are going to refer to those chemicals that are discharged, while the secondary pollutants or the secondary standards are going to be for those chemicals that form in the atmosphere from those chemicals that are discharged. All right, we'll put it down on paper soon, but it's important that you keep that in mind. And also, you have ever talked about drinking water standards, that we have primary and secondary standards, nothing to do. I'm not gonna go on it more, but if you already know, because I have seen that some students that already know about it, they get confused. No, do not confuse them. They are completely different to the air pollution. Okay, so another table that is gonna show you now California standards, and they're different. Many times California is more stringent. Sometimes it's just the same. It cannot allow higher concentration than national. National is the maximum concentration that could be allowed, and anything under will be fine if we can meet it. Technically, California has to put a lot of funding to be able to achieve stringent standards. That's why earlier in the year, I don't know if you heard that Trump was going to modify some funding for California because we were very harsh on the standards for air quality. So that was one of the things that was going to happen due to California investing much more on achieving these stringent standards. So, let's go back to carbon monoxide as we just talked. The national says that 35 ppm maximum in an hour, while California says 20 ppm. So it's 15 ppm less. It's a significant change, almost significant change in there, almost 30% of reduction on the exposure concentration in there. So similarly, you can check. So what are you going to do? You're designing something in California. You need to observe California standards. And if you observe California standards, you are always going to be meeting the national standards. But if you go somewhere else, another state, you need to observe the national standards and check if the state has different standards. Or if you're in a different country, because this is important too. Do not make the mistake of bringing US EPA standards and try to enforce that in a country that has no standards, so it's very loose, or maybe higher standards. So you need to remember, anywhere you go, you need to look for standards. Do not bring the standards with you. I know that you would like to get US EPA standards everywhere, but no, you need to always go and check what the standards are where you go. And that has happened with a lot of our students, because we have a lot of students from different countries, and no, you cannot use US EPA standards. Okay. So there is another index or parameter that is very important to provide information about the air quality, and is the air quality index, or AQI. In some counties, and if you're looking at the local channel, in the morning, usually in the morning, they provide information about the AQI. In some channels don't. So if you haven't seen this on the news or the weather channel, don't be surprised. It really depends on the local news or the local weather channel of the information, how they give it away. But the AQI is very important, and talks about all those contaminants of concern that are regulated, and you can see them on the top of the column, and it's just going to be related to a number. So 0 to 50 is going to be the smallest concentration, where air technically is good. You can go out there and you'll be fine. But as the number increases, the air quality becomes unhealthy. And then if you have a pre-existing condition, probably you don't want to be doing exercise or doing a lot of activities outdoors. So maybe in a problem, I can ask you, for this value, why would this be healthy or unhealthy, or describe the conditions of the air, giving AQI or giving the standards, and we're going to be doing problems. And actually, we have done problems already with a motorcycle, and we compare to the 9 ppmb. I don't know if you remember the problem in the chemistry part. So we have done some problems, not with the AQI, but with the air quality standard. So for the motorcycle, the carbon monoxide concentration came from this table, 9 ppm here, right here. So this is, we used this in the past. I just didn't bring it up because I didn't want it to throw a lot of new information at once and make you more confused. Okay, so what are the effects, the health effects or concerns? It's not only about health of humans, which is one of the most important things, right? We talk about toxic contaminants, particles that could be damaging our lungs. We have talked about acid rain and coming down into the acid coming down into trees or streams. And all those acids can also be damaging for trees and for historical buildings, especially in the olden times. Many of the buildings are or were built with calcium carbonate materials, and the acid rain is dissolving calcium carbonate. If you remember, calcium carbonate is alkalinity and tends to absorb hydrogens, and acid rain has high concentration of hydrogens. So they combine and the carbonates wash off, or they are dissolved. Technically, what happens is that they are dissolved, and that's what happens in there with the with this sculpture here is being like erased because of the dissolution of the minerals in there. So there is health, historical effects, and also ecological effects of the pollutants in the air. Any other? Yes, there is more effects. Ozone depletion we were talking about. We have a hole, or we had a hole of ozone close to the North Pole, and the ozone is a barrier that protects us from the UV light that comes from the sunlight. And if it is a hole in there, the UV can come through, and then we could get cancer. It's too intense for our cells and damage the cells and produces carcinogenic cells. Also, we are releasing a lot of emissions. The emissions are heating up the atmosphere, or the temperature in the atmosphere increases, and that is causing a bunch of disasters. We're talking about climate changing here, and the greenhouses that are releasing to the atmosphere are contributing to it. So the greenhouse effect comes from CO2, but can come from other gases like methane or the CFCs that are released from the AC units that we have and we need, and our refrigerators too. So there gotta be someone that is smart and wants to make a lot of money to find a different type of technology that can actually provide the same services but without the same level of contamination. Alrighty, so this is my cue to go to the whiteboard, to my iPad. You just let me stop in here. Is there any question while I'm changing devices? Any question? Any comment? Anything that you have seen that you want to share related to air pollution? Okay, so someone said no questions so far. Okay, good. So what I'm gonna do here is just put a, I know that you are doing your notes, but there is few, I have talked about several ideas and I wanna make sure that they're captured. So we're gonna put those in here. I'm gonna try to be very brief, as brief as possible, but just with the idea completely captured to ensure that you remember what is it that we talk about in class. So we talk about air pollution, and I have mentioned that we have indoor pollution and outdoor pollution. And both of them are as critical and as any of them. So there is not really which the outdoor is the worst one or the indoor is the worst one. I could tell you that some scientists say that the indoor pollution is more critical because in reality there is no regulation for indoor pollution except for changing your filters certified by HEPA. And if you don't change the filter, then your air pollution inside is going to be really bad. So it's a responsibility that we personally have. So since there is no regulations, no one going and checking, then many scientists say that, well, that's because of the users. Maybe they are not really doing what they should be doing. So what's in indoors that could be bad? We can have VOCs, volatile organic carbons, coming off from furniture, from the all the new things that we buy are gonna have some volatile organic carbons or VOCs coming off, unless you intentionally look for products that don't have that are VOC free. I know that
Professor?
Yes.
Are you writing on your whiteboard right now?
Oh, yes.
Because I don't know if it's just me, but I can't see anything.
I'm getting a white screen too.
Okay, hold on. Let me stop sharing. I didn't write a lot of things, by the way. But let me stop sharing my. Thank you for letting me know. Let's see. I'm telling you, I wasn't. There it is. Now using my iPad, right? Okay.
Now we can see it.
Yeah.
Thank you so much. So as you can see, I wasn't writing a lot of things, luckily. So the indoor pollution VOCs are going to be one of the major sources, and some people is very intentional looking for items, either furniture that is not treated with VOCs or paint, carpets, etc. Because otherwise they have VOCs in their formula, in the composition, in the production, and the way they were produced, and they are going to be eventually evaporating, and they're going to come indoors. We're going to be breathing them. Also particles or particulate matter. Particulate matter or PM are going to be very important. You need to make sure that you change those filters to ensure that the particulates are removed. Outdoor, we're going to have industrial emissions. And also we can have emissions from nature. Can you give me an example? Some emissions are naturally occurring all the time.
Volcanic eruption.
There you go, Kelsey. Thank you so much. Volcanic eruption.
What about CO2? Wait, that doesn't count as pollution, right?
CO2, yes, it is pollution.
Oh, okay.
Okay, someone is saying methane. Where is the methane coming from? Is that natural or is that industrial? From animals, methane from animals. Alrighty. Okay, so I really like these ones. Emissions from nature. So would you say that animal facilities will be considered nature or industrial?
I would say industrial because they're not necessarily like in nature. They're more like mass produced per se. So they're just like, I don't think it would happen naturally if they were in the wild.
Well, I think if they were on the wild, it wouldn't be that many. Probably maybe would be the concern. So we're gonna put the industrial emissions, right? As for example, farms, animal facilities. And here we can have methane, right? Methane being produced, released into the atmosphere. All right. Okay. What other type of industrial emission? Now that we went into industrial emissions, what else?
Factory emissions?
Factories, yes. Thank you. You gave me what I needed, Brian. Okie dokie. Anything else from nature?
Could it be like dust and pollen?
Yes, perfect. There is naturally dust storms in New Mexico. Have you heard about that? Dust in general. Let's just in general. And the dust storms in the Sahara that occurs too, just naturally, and that represents pollution. Okay. And then more examples. I'm not going to go to touch all the different examples in here. What I want to go now is point source and non-point source pollution, and using these examples that you gave me. Have you heard about point source pollution and non-point source pollution? No? Well, if you haven't heard about that, you're going to hear a lot about this in environmental engineering. The way that you do or propose your treatment is going to be related to the source of pollution being a point source versus a non-point source pollution. So let me use the example of the factory. If we go to a factory and we walk around the facility, do you think that you will be able to identify the place where they discharge the pollutants in the air? Just by visual inspection?
I think in certain factories.
In certain factories? But it's air, right? Gotta be something. If it is not, even if it's air with a different temperature, you will see the column of gas that it just looks different in density because of the change in temperature. So if you have ever been in a place where they do processing of the petroleum to produce gas, the refineries, have you ever been in one of those commercial industrial areas? No? Well, it's not a pretty place. So you can easily see the tower, and you can tell the emissions or the discharge of the pollutant into the environment very easily. If you can identify the point of discharge, and measure the amount, you can design a pollution control measure. What is a pollution control measure? Just a system that actually is going to be treating the gas. Okay, so if you can identify the point of discharge, You can measure the amount of the emission, and you can design a pollution control measure that is a point source of the pollution. So this is very, very easy. A factory is one example. Can you give me another example? One very close to you. There you go. Thank you. Someone in the chat is saying vehicles. Your car is a point source pollution. Why? Because you know where the emissions are released. And do we do anything to treat the gas before it's released into the environment? Or we just let the gas produced by the combustion of the gas go into the air?
Well, typically, car exhaust systems have filters in them to try and mitigate as much of the pollution that will be emitted. But at the same time, that's part of the reason why we have smog checks and stuff like that.
Yes, so that was coming on the chat. So the cars have air filters, right? To ensure that the air is filtered clean, and then we have a smog checks. So can you tell me, can you visually identify the point of discharge in a car?
Yes.
Can we measure the amount of the emission?
Yes.
Yes.
Yes, that's not visually, but we can take it to the smoke check and they will check the emissions, right? And then, is there any device designed to control or to ensure that reduce the emission of the car?
I think on cars it's called an exhaust manifold.
Okay, so it might be very specific technical terms, right? Also, you have to take the car for the regular maintenance to ensure that it's up to speed and doesn't start burning and inefficiently, and then releasing more toxic particles or decreasing the quality of the emissions in there. So yes, so it would not be fitting the definition of the point source pollution. Okay. Now, what is a non-point source pollution? What do you think that it is? You don't need to give me the definition. Give me an example. Whatever is easier.
Contamination in groundwater.
There you go. That's perfect. So let's put it contamination in groundwater. Why?
There might be multiple points of entry in the water table, or you can't identify exactly where it's coming from.
The contamination in the groundwater is underground. We don't know where it's exactly coming from. It's really hard to determine what is the hotspot. The hotspot would be the one with the higher concentration. So we're going to be blind with groundwater. And it's a non-point source pollution because it's going to be very difficult to know where it comes from unless we know that there is maybe we learn that someone spilled something on the ground and then we know they release. We know exactly what is going in there, right? But still, it will not be a point source pollution because it's going to be really hard to do something about it unless we can quickly excavate the soil and remove it and then mitigate it that way. But in reality, in general, contamination in groundwater is a non-point source pollution. Perfect. Any other?
Stormwater runoff.
A stormwater runoff. Yes. Why would that be a non-point source pollution?
Because the water travels across like urban areas and then it's discharged into one location, so you don't know what's in it or where it came from.
Exactly. A stormwater could be just going through different areas and dragging all the pollutants with it, right? And yes, there might be some ways to mitigate this pollution, but it's going to require a big, large land to do something about it versus the point source pollution that's going to be smaller, very well defined. So if you remember, I'm just going to give you the third one because we already have it on the board. It's going to be farms and animal facilities. So some of you are saying that there's going to be some methane coming into the air due to the animal production. Yes, the animals are going to be out there. We know exactly the area where it is, but we cannot really capture all the methane from the cows and treat it and remove the methane and use it for energy, right? Because it's just out there, it's too much land. So when we are talking about a non-point source pollution, we have an idea of the area where pollution occurs. But it is difficult to quantify. Okay, it can be coming from many different places. It can be many sources. It can be moving, like the cows. Okay, and then it's gonna be hard. It is difficult to have a central treatment. So what do we do? How do we do this? Well, every cow is gonna have an average discharge of methane, and if we have 2,000 cows, we have a limit on the discharge of methane. And if for any reason I have more cows because I want to make more money, then I need to pay some money because I'm exceeding the limit of discharge. So it's kind of ishy-wishy. In this non-point source pollution world, sometimes whoever is contaminating in a situation like this or responsible for such type of pollution, they need to pay a fine, or someone that is not contaminating as much pay to that person, because then it's going to be getting credit for that person that is not contaminated as much. So if you really like politics, you're going to love the non-point source pollution world. It's a lot of trade-off and exchanges of credits for the pollutants that are released or not released in a given time. So they're going to be there's going to be permits depending on what is that is happening. So does it make sense now? Is a point source and non-point source pollution? Right? Thumbs up. No, there is no thumbs down. Only thumbs up, right? Okay, some of you are saying yes on the chat. Perfect. All right. So let's talk about emissions, and we talk about primary pollutants and secondary pollutants. Just to make sure that is on your notes, we have primary. Why do we say that's the primary pollutant? The one that is directly
discharge.
Thank you. Directly discharge in the air, and then we're going to have a secondary pollutant. And how do we differentiate them?
Secondary pollutants are the result of primary pollutants and their reaction with the atmosphere.
There you go. They are formed in the atmosphere. Thank you so much. How are they formed? Due to reactions. They can be chemical or physical. Physical reactions. Okay. So chemistry is always going to be with us. So I'm going to be changing the page. Is everybody okay with this? Everybody has it down? Yes. I have the tiles, most of the tiles up, so you give me thumbs up, that will help, or maybe the chat. Alrighty. Okay. I'm gonna be checking with you. Someone told me today in office hours that sometimes I'm going too fast and you miss things. So before I change, I'm gonna be checking. So someone is asking if acid rain will be falling as a secondary pollutant. What do you think?
Yes.
Why?
Because acid rain would be the result of carbon monoxide, sulfates and sulfides, and the reactions in the atmosphere.
Yes, perfect. So that was a very good question, and thank you so much for the answer, Samuel. So yes, it's a secondary pollutant because it forms due to the reactions that happen there. Alrighty, so I'm gonna change now. I saw the thumbs up. Page number 2. So I don't think that I mentioned this, but I think that it's very important to put in here that the pollution is categorized by the way it has been created, the pollutant emissions. So, or pollution emissions can be classified by how they were created. And one of them is going to be to combustion. And we have talked about that already. The cars and the combustion of the gas or the fuel. It could be evaporation, and we have talked about that too, VOCs, right? And this is just more making it very, very specific. And the last one that we also have talked about it is grinding of abrasion, and that's formation of particles from solid particles. So the PMs, the particulate matter, can be formed due to the grinding. Oh, hold on, sorry. Grinding. This is weird. And abrasion. So these are the 3 different ways that we could get those particles in the atmosphere or indoors even. The source of pollutants we already talked about them. This is just slightly different. Could be mobile and stationary. Can you give me some examples of mobile or stationary? Just think about the air. What is moving?
Mobile cars.
Cars, railroads. Well, let's put it in here. It's trains, ships, planes. What about cows? Cows move around, right? And what's stationary? Factories. Okay, what else? Power plants.
Gas stations.
Gas stations, yes. Or homes are stationary. Oh, you got it. Someone said as soon as I said it, it was coming in there. We were thinking of like homes. Homes are stationary too, unless they are how do you call those that you drive around? I forgot. Well, you know what I'm saying. Those moving homes.
RV.
RVs. Yeah, thank you. Like I was escaping. And the farms, right? Farms and all the agriculture facilities, etc. So there is a bunch of things that cause air contamination. Okay. Who can tell me the 3 different things that we talk about in terms of the air policy or regulations? No? Remember that we talk about the Weather Channel?
Are you talking about today or a different?
Yeah, today, just a few minutes ago when I had the PowerPoint up.
The National Ambient Air Quality Standards.
Mm-hmm.
National emission standards for hazardous air pollutants.
Okay. Oops. And what was the last one? Next. NESHAPs. And what is the last one? Anyone remembers?
Was it the California standards? Or...
Well, we can say California standards too. CA standards next to the national air quality standards, right? And that parameter that sometimes is given in the local stations, weather stations, or
AQI.
AQI, air quality index. So these 3 are, all of them are under Clean Air Act. Okay. Established in the 1970s. All right. So I'm telling you, I'm putting everything together just to ensure that you can go back and remember what we talk about. Alrighty, so now we're moving from air quality standards, we talk about indoor pollution, and we talk about point source, non-point source pollution. I'm gonna be taking you to the point source pollution world, and I'm going to be classifying the ways of pollution control or the type of treatments or technology that can be used, solutions that can be used to control contamination coming from point source pollution. So this is going to be the air pollution treatment and control for point source. Factories, okay, that will be an example. And I'm just gonna leave it in there. One is gonna be gaseous. And the second one is gonna be the particulate matter. So let's talk about first the gaseous one. I'm gonna put them in here a list, and then we're gonna go to the slides again to show you the photos on how they look like, and then we're gonna be doing the design of 2 types, one for the particulate matter, and then actually for both of them are gonna be for particulate matter. So for gas, how do we remove gas from air? We have wet scrubber, is the most common one. I'll show you what that is. It's very common in the wastewater environment because there is a lot of odors that contain volatile organic carbon, and they have to be removed from the air so it doesn't go out and increase the sea, not only the odor for the community, but the gases that will contribute to the warming of the atmosphere. And then we have adsorption. Activated carbon, especially powder, is a very good media to remove organics. Also, we have flue gas, desulfurization. fluidization. And then combustion. It's not ideal. Combustion has other emissions, but also we could do condensation. Some of the gases can be condensed and then just captured as liquids, and that would be an easy way to remove them from the air. And then we're gonna address particles or particulate matter.
Professor?
Yes.
What does it say under C?
Combustion?
No, C.
C.
Part C, right after B.
This one?
Yeah.
FLUE, flue gas.
All right, thank you.
And then for the particulate matter, we're gonna have cyclones. Cyclones are just towers that are gonna be spinning the air, and that is gonna be producing different velocities for particles and air. They're called collectors, cyclones collectors.
Oh, Dr. Palomas, maybe you could scroll up to like number 1.
Yes.
Yeah. Okay, that helps.
Yes. No, I push it up most of the time because then my hand is below the outside of the iPad, and I tend to erase, and I don't know how that works.
What did it say above it where it said gaseous? I don't know if I got that down.
It's gaseous. Yes, it's gas.
Was there anything above that though? Oh, okay. There we go.
All right. Then we have fabric filter. Have you ever used a vacuum cleaner? Yes?
Yeah.
Nope.
Yes, of course.
At least seen it? Well, it's similar to a vacuum cleaner. Very, very similar, especially the older ones, the ones that my mom had when I was little, long time ago. It's very similar to that one. You could take the bag out. These fabric filters have bags in there that you can just exchange when they're full. And the numbers is going to be the Venturi or Venturi scrubber. It's a combination of the principle of the wet scrubber with the Venturi. And then we're going to have an electrostatic precipitation. And then finally, sedimentation or gravitational settling chambers. And this settling chamber, the principle is exactly the same principle that we will use later to design settling basins in water treatment or for wastewater. So it works for any fluid, just a slightly different density of whatever the fluid that we're working with. So again, these are different pollution control measures or systems for air pollution, for gaseous or gas, and the particulate matter. Right? And what are the sizes that we're going to be looking into remove from the air? Remember the size?
0.5 and 10.
2.5 and 10 micrometers. Remember the units. Sometimes on the test I have asked what is the unit associated with the 2.5 and the 10, and the students are always given meters. I'm like, oh no, that cannot be a particulate matter, right? Just think about the unit. It's micrometers. Okay, so I just got out of the whiteboard, and let's go back to show you the different ways of treating the air with photos. And then we're going to be able to do it today, but we're going to be doing some design problems with it. All right, so I'm going to go to the laptop now. see it. All right. Okay. So we talk about the two types of pollution control, gaseous and particulate matter. Now we are going to show you how they look like. Moving. This is the wet scrubber. There is, nothing fancy inside. There is a lot of things happening. And the great news for us is that all of this is commercially available. So we don't really need to design or size the tower. We don't need to have an idea of what size we need based on the flow, how much air we're going to be treating, and what is the concentration of the contaminant that we want to remove. We do need to know that, but we're going to be working with the vendors of this equipment, and we're going to tell them this is the air quality and this is the flow rate of my air, and they're going to be working with you, helping you selecting the best size. You're going to be telling them if you have any restriction of space where you are working, or depending on the area that you are, is indoors, is outdoors. They're going to be telling you about the requirements of ventilation. So in terms of design, it's going to be a lot of work with the vendor. And you just need to know some of the flow, the concentration, the type of pollutant, and they're going to be telling you what's inside. Now, be very careful. They're not the ones telling you what to use. They're suggesting you as an engineer, you need to know the chemistry and the type of contaminant that you have, the wet scrubber, the way it works, and you will know if you know about the properties of the chemical, if it's going to be working for you. It has a pool of a liquid, may or may not be water. It could be also a liquid that could be acidified or as basic, depending on what the chemical is coming in. Your airflow is going to come from the bottom of the air scrubber. It's going to come through the water, and as it goes through the water, the gas that you want to remove from the air is going to be left behind in the water. There may be some droplets that are going to be coming up with the air, and that's another bed of media that is going to be removing those droplets of liquid, and also any gas that might be staying in that liquid. And then finally, there's going to be another layer on the top. It says very small, but it says C is like a mesh that is also going to be helping you drying or removing moisture from the air before the air is released at the top of the device. So it's very simple process. The only thing that you need to take care of is knowing what's the liquid, what's the material in the packing in there, just to make sure that that's what you need for the gas that you are trying to remove from the air. And also, what is the removal? Based on your concentration, you may or may not achieve the removal. So don't think that you need to design for 100% removal. What will be the number that you need to design for here at the outlet in this tubing that says B? Do you want to get all the way down to 0? How low? I don't know. I know you don't know a chemical specifically, but what number will be here for you to do your design?
Standard.
Standards. Yes, you need to be looking at the standard. Okay. Are the standard, or maybe this company has a permit that allows them to discharge this amount per year, per day, per month, and based on that you back calculate how much will be discharged depending on the flow that you're discharging and for how long, etc. And so it's important that you keep that in mind. All right. This is another image of a wet scrubber, a simpler one. The air goes in there on the bottom. There is a pool of solution in there that is going to be scrubbing, right? Scrubbing the gases. And then the air continues up through the packing, whatever the packing is, and the meshes to eliminate the moisture, and finally goes up There's a very simple way to put it. Just important to know the details of what's in the packing. There is another way of treatment, and we already talked about this. Adsorption with activated carbon. Adsorption with activated carbon is going to be one of the easiest ones to go. In this case, you will need to size the size of your tank or your system. Some of the companies actually already have those commercially available, and you will just need to say, depending on your flow and the chemical, you will need to calculate based on the givens from your vendor, what will be the absorption time before you exhaust the bed in the carbon, and then see if you can clean it and recover it. Usually that's going to be done, or you need to remove it and just incinerate it. And combustion is the next way to remove something from the gas. I don't think that this is the best way to address. Usually going to be volatile organic carbons. They need to be ignited to be able to go to combustion, to be removed. And I have seen actually, I don't know if I've shared with you, I am from Mexico, and combustion of the gases that could be oxidized on air was one of the most common ways of removing them from the air when I was back in Mexico. So I don't think that is really friendly for the environment, but it's done. Desulfurization is just the removal of the sulfur from the gas going into the air. Why do we want to remove the sulfur from the air, or that is before it is released into the atmosphere?
Because doesn't sulfur have adverse effects on ozone and things like that?
Because of sulfur, it could have adverse effects on ozone, but also it's going to be combining with any hydrogen and forming H2SO4, which is the acid rain. So it's the sulfur can be very detrimental in the atmosphere because of that. And the last method is condensation, a very easy no-brainer, right? If condensation is cheap, it sometimes takes a lot of energy. You need to change temperature. Changing temperature is always very expensive. So it really depends on what would be the best method depending on the chemical, and also we need to consider the financial situation of whoever is your client. The good news is whenever we do this type of treatments, we're going to have a vendor that is going to be working with us and selecting the best option. And then if you're working in this type of pollution control devices, you're going to have a senior engineer working with you, and probably they're going to be guiding you on what would be the best one. Many cases, the young engineers are going to go and doing the search and talking to vendors, and the senior engineer is going to come and deciding which one to go after having all the information down. Or maybe you're working in public, you might be looking into whatever the engineers bring you, and then you need to know which one might be better. You know your city, you know the facilities, and maintenance is going to be very important that you keep in mind if you're on the public side. Maintenance and operation, what kind of operator you need, the grade, and how often you need to clean something. So the young engineers, when they're doing this type of design, they need to provide a maintenance and operation guide, all right, for the client. So you could be either on the client side or you could be on the team that is designing. So let's talk about particles. Particles, it's a physical process because we have particles, and many, we have an advantage when it's related to air. We can easily trap the air in one of these two systems, the cyclone or the fabric filter, and just induce through flow the removal of these particles. The fabric filter on your left is right here. You notice this is, here I'm showing you, let me see. Here, I'm not showing you. Okay, my pen is not working, I don't know why. No, it's not working. I'm sorry. I was trying to use a PowerPoint tool to show you. On the center, we have the bag. we have the bag that shows you that from the bottom, you can see that the air goes through and the particles are going to be stuck inside of the bag. Once the particles clog the bag, then you're going to need to change it. And the capacity of the filter is going to be depending on the flow, the concentrations of the particles. That should be on the specifications given by the vendor. The amount of flow that you're going to be treating is going to determine the size of the bag. So every bag is going to have a given filter capacity. Based on capacity and based on the flow that you're treating, you're going to be determining the number of bags. So it's going to be very simple calculation to design the size of your system. In the cyclone, again, it's also very easy system. The air comes inside. It's going to be spiraling down. And why it's going to be going down? Because the air, because it's lighter, while the flow is going to try to, the pressure is going to be trying to taking it down. What it's going to be doing is pushing the particles that are affected by gravity down and precipitated and collected in drums or sometimes trucks. And then the air, because of it's lighter, is going to go back up and escape through the outlet. So pretty simple, nothing fancy. Just again, depending, the size is going to be selected based on the flow, the amount of flow that you are treating, and also the particle size. So you need to be working with your vendor and looking to what is the size that is appropriate to treat or remove from a given device, or maybe you have the particle size and you will know directly and go in and look for the system that is going to be giving you that. Now here on the right, I want to show you the Venturi scrubber. It's very similar to water resources. If you have taken the water resources, no, actually it's fluids class. Now we do it in fluids. In fluids is when we talk about ways to measure flow. A Venturi meter is one of the best ways, calibrated ways to measure flow. So the Venturi meter is used for that, but not only for that, because of the reduction on the cross section, it increases the velocity. And by that change of velocity is the way that we can estimate the flow. So by increasing the velocity here, it's going to be inducing changes in the way that the particle and the contaminant and the gas are interacting, and it's going to be allowing us to separate them just by that change of velocity. And the other exciting one is the electrostatic precipitation. Very simple. There's some plates. Those plates are connected to current. There is energy always going or current going through the plate. And as the airflow is going to be moving from one side of the plate to the other side of the plate, those particles, because most of the time they have a charge. If they have a current in there, they're going to be just going and sticking into the plate and remove from the air that way. So it's more expensive, but if there's very fine particles that are charged, is one of the most efficient ways to remove these particles and then just comply with the standards or the discharging limits depending on the type of industry that you're working with. And how do you remove those particles from the plates? Well, the only thing that they need to do is stop the current, and as the current stops, the particles drop down, and you can see the bottom of here of the device. There is a collection area where they can be put in a drum and then or in a truck. Sometimes there is a big, the back of the truck, a big bin in there that is just collecting everything, and then once it's full, close and send out for disposal. So these treatments are very, very easy to understand. And okay, we're going to stop here because we're going to do a problem. We have 6 minutes. Yeah, we can start the problem. Questions so far? No questions? Okie dokie. Okay, we have a comment on the chat. Oh, no questions. Okay, thank you so much. So now you're seeing that we're going to design, we're going to start sizing or looking into how many or how big, depending on the flow, what is the concentration. Yes, we're going to be needing to use chemistry to size or to determine quantities, but it's going to be way more practical. We're going to be using that chemistry to help us on our decisions. So now, there is a bunch of practice problems, or in this case, is solve problems. There is a bunch of solve problems in your textbook that I want you to start looking at, especially these 7.1 to 7.7. Later, the other problems that I'm actually putting in there some details, like 7.11, the speed change with elevation, or downwind ground level concentration. All of that we're going to be talking about in the next section once we do the design problems. But you can start looking at some of the solved problems that are there. Okay? So let's go to the settling chamber. This problem is really fun. I really like it. We're going to be actually sizing something to treat some air. So it says in here that we have, let's read the problem. We don't have a lot of time, but we have time to understand. We have to design a settling chamber to collect 50 micrometers in diameter particles, and they have a 200 kilograms per cubic meter density. So we need to know some properties of those particles. They are in an airstream with a volumetric flow rate of 1.5 cubic meters per second. The chamber is to be 2 meters. This is width, no width. Okay, that's a typo. And 2 meters high. So we have some of the dimensions. What we need to do is calculate the length of this chamber to give theoretically a perfect collection efficiency. That means 100% removal. So this perfect collection efficiency will mean that we can remove all the particles 100%. Why do we know the chamber width and height? Probably that's going to be commercially available, and you can just cut the length or give the length that you need to your vendor, and they will, based on the cross sections that they have available, then they can customize your length based on the type of particles and the flow that you're treating. That's why we need to design for the length. And then that's part A. Part B will be determine the collection efficiency for particles of the same density, but they are 25 micrometers in diameter. So this problem is completely different. Now with this chamber design, if there's particles that are smaller, half of the size, 25 micrometers in diameter, that come in, they have the same density, what will be the removal efficiency? So in this problem, we're going to be looking at two different things. The first part in part A is going to be doing the design. Designing something to remove for a given particle. In the second part, we are going to evaluate an existing system, and if another particle comes, is it going to be removed and how much is going to be removed? All right, so sometimes you're going to be able to go on and do some assessment of the existing things. You can make money out of that too. So that's why we're looking at these two parts of the problem. All right. We have 2 more minutes. So maybe it's 1 more minute. So no, I'm not going to draw the system right now because I don't want to, I'm going to be asking questions. Let's just stop it in here. We'll continue on Monday. We're going to have a very busy Monday. Teams presenting, solving problems, and then quiz. I'll be here for another 2-3 minutes. Let me know if you have any questions. I'm going to stop and have a great weekend.